Bismillah ar-Rahman ar-Rahim. This is the first lecture in the chemistry of carbohydrates. We start with the objectives of this lecture. أهداف محاضرة اليوم. These are to define carbohydrates, to show the classification of carbohydrates, to describe monosaccharides, to verify the types of isomerism, and finally to describe the reactions of monosaccharides. We start with the definition of carbohydrates. Carbohydrates are polyhydroxyaldehydes or ketones, or substances that yield such compounds on hydrolysis. This is simply the definition of carbohydrates. Many but not all carbohydrates have the following formula. In fact, the common formula for carbohydrates is written in different ways. However, the common property that's shared by these different forms of the formula is that the number of atoms of carbon and oxygen are equal, while the number of hydrogen atoms is double than that of carbon and oxygen. Some carbohydrates also contain nitrogen, phosphorus, or sulfur. Carbohydrates are also called saccharides or sugar. Why? Because the simplest carbohydrates, they have a sweety taste. Now we discuss the classification of carbohydrates. تصنيف السكريات. Carbohydrates are classified into four major groups: monosaccharides, disaccharides, oligosaccharides, and polysaccharides. Monosaccharides are also called simple sugars, as they cannot be hydrolyzed to more simpler carbohydrates. They can be also subdivided further depending on several points. First of all, we can categorize or classify monosaccharides depending on the number of carbon atoms they contain. For example, trioses, they are monosaccharides containing 3 carbon atoms. Tetroses, they are monosaccharides containing 4 carbon atoms. Pentoses, they are monosaccharides containing 5 carbon atoms. Hexoses, they are monosaccharides containing 6 carbon atoms. For example, glucose. Glucose is a hexose, etc. Secondly, we can classify monosaccharides depending on the site of carbonyl group. If that carbonyl group is free or terminal, then the monosaccharide is an aldehyde and it is called aldose. For example, glucose is an aldose. It is called aldohexose because the carbonyl group is terminal and it contains 6 carbon atoms. Or if the carbonyl group is not terminal, not free, then the monosaccharide is a ketone and it is called a ketose. For example, fructose is a ketose, also called ketohexose. Why? Because it contains 6 carbon atoms and the carbonyl group, it is not terminal. Secondly, disaccharides. These are the carbohydrates that contain 2 molecules of monosaccharides joining together by glycosidic bond, or also can be defined as the sugars or the carbohydrates that yield 2 molecules of the same or different monosaccharides on hydrolysis. Examples of disaccharides are the lactose, the maltose, and the sucralose. Thirdly, the oligosaccharides. Oligosaccharides are carbohydrates containing 3 to 10 molecules of monosaccharides, or also can be defined as that carbohydrates that yield 3 to 10 molecules of monosaccharides on hydrolysis. Example of oligosaccharides is the maltotriose, which contain 3 glucose molecules. Polysaccharides, these are carbohydrates that contain more than 10 molecules of monosaccharides, also can be defined as that carbohydrates that yield or result in more than 10 molecules of monosaccharides on hydrolysis. Therefore, polysaccharides are a polymer of monosaccharides. Polysaccharides can be further subdivided into homopolysaccharide when the polymer when the polysaccharide polymer consists of the same monosaccharide units. Example, starch and glycogen are homopolysaccharide because they contain only glucose monosaccharide. With heteropolysaccharide, it is a polysaccharide polymer consists of different monosaccharides units or their derivatives. For example, hyaluronic acid and chondroitin sulfate are examples of heteropolysaccharide because they are consist of different molecules of monosaccharides or their derivatives. Now we start with the monosaccharides. They are the simplest carbohydrates that cannot be hydrolyzed to a more simpler carbohydrates. Example of monosaccharide: glucose, fructose, mannose, and galactose. They have the same chemical formula. That's C6H12 and O6. And we see that the number of carbon and oxygen molecules are equal, while the number of hydrogen atoms is double than that of carbon and oxygen. This figure shows different types of monosaccharides, including glucose. This is the chemical formula for glucose, mannose, galactose, and these are other monosaccharides. Glucose, we talk few words about glucose. It is the most important carbohydrate. Most dietary carbohydrate is absorbed into the bloodstream in the form of glucose. Also, other organs, also other sugars in the body are converted into glucose in the liver. Glucose, it is the major metabolic fuel in the body, هو المصدر الرئيسي للطاقة. It is the precursor for the synthesis of all other carbohydrates in the body, including the glycogen for storage and the ribose and deoxyribose. In other words, glucose is the precursor for the synthesis of these pentose sugar that are included in the synthesis of nucleic acids. The asymmetric carbon atom, it is that carbon atom to which 4 different atoms or groups are attached, and the presence of asymmetric carbon atoms allows the formation of isomers. This carbon is asymmetric. Why? Because to which 4 different atoms or groups are attached. Isomerism. Sugars show various forms of isomerism. Isomerism means spatial configuration, الترتيب أو التكوين المكاني. Compounds that are identical in composition. In other words, they are identical in their chemical formula. but they differ in their spatial configuration, are called stereoisomers. And definitely monosaccharides are example of stereoisomers. As I said, the presence of the asymmetric carbon atom allows for the formation of isomers, and the number of the isomers depend on the number of asymmetric carbon atoms present in the molecule. What are the types of isomers? The first type is D and L isomerism. D for dextro and L for levo. This type of isomerism depends on the orientation of hydrogen and hydroxyl groups around the carbon atom that's adjacent to the terminal primary alcohol carbon. For example, in glucose, it depends on the orientation of carbon number 5. Why? Because in glucose, the terminal primary alcohol carbon is carbon number 6. Therefore, the carbon atom next to it is the carbon number 5. When the hydroxyl group on that carbon atom is on the right, then the compound, it is called D-isomer or dextro. And when the OH group on this carbon is on the left, then this compound is levo or L isomer. In fact, the vast majority of sugars in the human body are of the dextro sugars. If we take glucose an example to illustrate the D and L isomerism, this is the D glucose and this is the L glucose. As I said, the categorization whether the compound have a D or L isomerism, this depends on the orientation of the carbon which is adjacent to the primary alcohol carbon. Therefore, in glucose, it is the carbon number 5. When the OH group on that carbon is on the right, the glucose is called D-glucose. While when the hydroxyl group on that carbon lies on the left, the glucose is of the levo type. The vast majority of glucose in the body is in the form of D-glucose. And if we see the chemical configuration of that glucose molecule, we found that they are mirror image of each other. The second type of isomerism is the alpha and beta anomers. Less than 1% of monosaccharides containing 5 or 6 carbon atoms exist in the open chain or in the acyclic form. Rather, they are predominantly, in other words, more than 99% of monosaccharides, they exist in a ring structure, in cyclic structure, in which the aldehyde or the ketone group react with an alcohol group in the same molecule of sugar. If the product of that reaction between the aldehyde and the alcohol group in the monosaccharide, if the result is a 6-membered ring structure, it is called pyranose, and this contains 5 carbon atoms and 1 oxygen. For example, glucopyranose. While if the result is a 5-membered ring structure, it is called furanose, which contains 4 carbon atoms in addition to 1 oxygen. And for glucose, the 5-membered ring structure, it is called glucofuranose. And the 99% of the ring structure of glucose molecule is in the form of pyranose, in the form of 6-membered ring form. This is the pyranose form and this is the furanose form. As I said, the pyranose form is a 6-membered ring structure containing 1 oxygen and 5 carbons. This is the oxygen molecule, and these are the 5 carbons. 1, 2, 3, 4, and 5. And this is the 6th carbon molecule of glucose, because glucose containing 6 carbon atoms. And this is the 5-membered ring structure, the furanose. And for glucose, it is glucofuranose. It is a 5-membered ring structure containing oxygen and 4 carbon atoms. Carbon number 1, 2, 3, 4. And this is the 5th carbon atom of glucose, and this is the 6th carbon atom. As I said, most monosaccharides exist in cyclic form as they contain 2 functional groups, the carbonyl and the hydroxyl groups. And also, as I said a few seconds ago regarding glucose, more than 99% of glucose is in the form of a 6-membered ring structure called pyranose, where the carbonyl group at carbon number 1 react with the hydroxyl group at carbon number 5, forming the pyranose form. This is the pyranose form. Here there are 2 different forms of glucose. This depends on the orientation of the hydroxyl group of the anomeric carbon, of the carbon number 1. If the hydroxyl group extends to the right, in other words below the ring, the compound is of the alpha, and it is called alpha-D-glucopyranose. While if the hydroxyl group extends to the left above the ring, the compound it is of the beta type, and it is called beta-D-glucopyranose. This is the alpha-D-glucopyranose. Why? Because the hydroxyl group of the anomeric carbon at carbon number 1 lies to the right or below the ring, while with beta D-glucopyranose, the hydroxyl group of the carbon number 1 of the anomeric carbon lies above the ring or to the left. The third type of isomerism is the formation of epimers. And by epimers we describe 2 monosaccharides that differ in the configuration of hydroxyl and hydrogen around only one specific carbon atom apart from the carbonyl carbon. Let us give examples of epimers. The glucose and the mannose molecules are identical with the exception of the orientation of hydroxyl and hydrogen around carbon number 2. In glucose, the hydroxyl group lies to the right, while with mannose the hydroxyl group lies on the left. Therefore, glucose or mannose are epimers at carbon number 2. Let us take another example. Glucose and galactose are epimers at C4. Why? Because glucose and galactose, they have the same chemical formula and their molecules are identical with the exception of the orientation of hydrogen and hydroxyl at carbon number 4. In glucose, the hydroxyl group lies to the right, while with galactose, the hydroxyl group lies to the left. The fourth type of isomerism is the aldose and ketose. Fructose and glucose are monosaccharides. They have the same chemical formula, but they differ in the site of the carbonyl group. In a glucose, the carbonyl group is free or terminal. It is present at C1. Therefore, a glucose is an aldose, and it is called aldohexose because it also contains 6 carbon atoms. In a fructose, the carbonyl group, it is not free, it is not terminal, it is present at carbon number 2. Therefore, it is a ketone, and it is called ketose. And the fructose, it is a ketohexose because of 2 reasons. The carbonyl group, it is not terminal, it is present at C2, and because it contains 6 carbon atoms, therefore it is a ketohexose. For glucose, it is a reducing sugar because of this property, because it have a free or a terminal carbonyl group. While fructose, it is a non-reducing sugar. Why? Because it have no free or terminal carbonyl group. Now we discuss the reactions of monosaccharides. We start with the oxidation reactions. We have 3 types of oxidation reactions of monosaccharides. If the carbonyl group of an aldose is oxidized by a mild oxidizing agent to carboxylic acids, the result is an aldonic acid. For example, if the aldose is glucose, and if there is oxidation of the carbonyl group of glucose, the resultant is gluconic acid. It's an example of aldonic acid. The second type of oxidation reaction is the oxidation of the primary alcohol group, resulting in the formation of uronic acid. And if glucose is oxidized in this way, that's if the primary alcohol group of glucose is oxidized, the result is the glucuronic acid, and for galactose, galactouronic acid. The third type, where both groups, the carbonyl group and the primary alcohol group in an aldose, is oxidized, resulting in the formation of aldaric acid. For example, the glucose is glutaric acid. In other words, glutaric acid is a glucose where both the carbonyl and the primary alcohol groups are oxidized. This figure shows the oxidation reactions of monosaccharides, taking glucose an example. If the carbonyl group of an aldose is oxidized, this results in the formation of aldonic acid. And if we take glucose an example, the result is gluconic acid. While if the primary alcohol group is oxidized in an aldose, a monosaccharide, the resultant is the formation of uronic acid, and for glucose it is called glucuronic acid. While if both groups are oxidized, the carbonyl group and the primary alcohol group, the resultant is the formation of aldaric acid, and for glucose it is called glutaric acid. The second type of reactions of monosaccharide is the reduction reactions. Aldoses and ketoses can be reduced, forming sugar alcohol called alditols, where there is reduction of the carbonyl group of monosaccharides. What is the biomedical importance of sugar alcohol? Several of them are used as a sugarless sweetening agent. For example, sorbitol or glycositol and mannitol. Also, they are important components of lipids. Sorbitol also used as a laxative ملين. Fourthly, mannitol is used to reduce acutely raised intracranial pressure after head trauma بعد إصابات الدماغ. And the fifth point is mannitol is also used to treat patients with oliguric renal failure, to increase the renal perfusion. يستعمل في حالات عجز الكليتين، خصوصا عجز الكليتين الحاد. The third type of reactions of monosaccharides is the glycosides formation. Monosaccharides can be joined to form disaccharides, oligosaccharides, and polysaccharides. And the bonds linking these sugars are called glycosidic bonds. And the enzymes catalyzing the formation of these bonds, the glycosidic bonds, are called glycotransferases. Glycosides are formed by the condensation between the hydroxyl group of the anomeric carbon of monosaccharide or monosaccharide residue and a second compound that may or may not be another monosaccharide. In other words, the glycosides result from the condensation combination between the hydroxyl group of the anomeric carbon of a monosaccharide, of hydroxyl group of carbon number 1 of a monosaccharide, and the second compound that may or may not be another monosaccharide. If the second group is a hydroxyl, then the resultant bond, it is of the O type. It is called O-glycosidic bond. While if the second group is an amine, the resultant is an N-glycosidic bond. So, the O-glycosidic bond, it results from the reaction between the hydroxyl group of the anomeric carbon atom. This is the anomeric carbon atom, the carbon number 1, and with a hydroxyl group of the second compound. All sugar glycosidic bonds are of the O type. They are O-glycosidic bonds. For example, this is the disaccharide maltose. It is linked by it consists of two molecules of glucose linked by O-glycosidic bond. Why? Because this bond, it is formed by the reaction between the hydroxyl group of the anomeric carbon of a monosaccharide with the hydroxyl group at the carbon number 4. This is another example of O-glycosidic bond, but it occurs between a sugar and amino acid, where there is a reaction between the hydroxyl group of the anomeric carbon of a sugar with the hydroxyl group of another compound. Here it is the amino acid serine, forming O-glycosidic bond. The N-glycosidic bond, it results from the reaction between the hydroxyl group of the anomeric carbon of a monosaccharide with amino group. For example, the adenosine, which is a nucleoside, result from the, it is made of adenine and pentose ribose. these two compounds are linked by an glycosidic bond. Why it is called an? Because it is a reaction between the hydroxyl group of the anomeric carbon of ribose and with the amino group of the base adenine. Another example of the N-glycosidic bond is the reaction between sugar and amino acid, where there is here a reaction between the hydroxyl group of the anomeric carbon of that sugar with the amino group of this amino acid asparagine, forming that N-glycosidic bond. Therefore, naming of that bond, whether N or O, depend on the type of the second group that's linked to the hydroxyl group of the anomeric carbon of monosaccharide. If the second group is a hydroxyl, the bond it is called O-glycosidic bond. While if the second group is an amino group, then the bond it is of the N-glycosidic pi. Now we come to the naming of the glycosidic bonds. These bonds linking between sugars are named according to the number of the connected carbon atoms and to the position of the anomeric hydroxyl group, to the orientation of the anomeric hydroxyl group of the sugar involved in the bond. If the anomeric hydroxyl group is in the alpha configuration, then the linkage is an alpha bond, while if it is in the beta configuration, the linkage is of a beta bond. Let us take this example, the disaccharide lactose. Lactose is a disaccharide consists of galactose and glucose monosaccharides. And the linkage in disaccharide, it is of beta 1,4. Why it is beta 1,4? Let us describe the type of linkage between glucose and galactose molecules in the lactose. The O-glycosidic bond in lactose is formed between carbon number 1 of galactose and carbon number 4 of glucose. Therefore, it is 1,4. 1 for the carbon number 1 of galactose and 4 it is for the carbon number 4 of glucose. Why it is called beta? Because the hydroxyl group of the anomeric carbon of galactose, it lies above the ring or to the left. Therefore, it is called beta. Therefore, the linkage in lactose, it is of beta 1,4. And lactose, it is therefore called galactosyl beta 1,4 glucose. And thank you for listening.